Okay, kiddos, here's part 3. So, whoa there, cowboy. There was a lot of information on that the second page. So let's slow it down a little bit and work through some examples. Question 1 says, a 500 gram mass hangs from a spring, and then in parentheses, K equals 50 newtons per meter. So our spring constant is 50 newtons per meter. First, we're going to draw a diagram. Well, we can do that. So it's hanging. So we have the ceiling, and we have the spring, and we have the mass. Instead of M, maybe we would write 500 grams. And next to the spring, we could write something like K equals 50 newtons per meter. Alright, how much would the spring stretch when the mass hangs from it? So, if the spring were just sitting there, it would be unstretched completely. And if the mass were attached to it, we all of a sudden have this force pulling on the string. And that force would be the weight of the mass. So we know that weight is mass times acceleration due to gravity. So we could say that the weight of the mass is what pulls on the spring, and M, so that is half a kilogram, 500 grams, right? We go whoosh, whoosh, whoosh. Hey, where's my 1, 2, 3, like that. G, so 9.8 meters per second squared. So this is mg, and we say it's equal to negative k, and then x for the displacement. That would be how much it's displaced. And what do we get? How much would the string? Oh, that's what we're looking for. So, whoops. Great. What did we say? So weight equals force equals mass times the acceleration due to gravity. And I'm going to write out the formula like this: negative k, which is what we have, so 50, and then x, displacement. So in dealing, you can basically forget about the negative sign in front of the k. In the previous video, I explained where that comes from. But you know, you might have to overthink sort of the direction and whatnot. So if we just forget about that negative, let's see what happens. Well, it's going to work. So, all right, and if we were to divide, let's see, I think we would get, wait, 980, that sounds totally wrong. Okay, no, I'll use the calculator. 0.5, so 4.9 over 50, oh yeah, that sounds much better. Divided by 50 equals, and we get 9.8 centimeters, or 0.098 meters. What that means in terms of us, 9.8 centimeters. So this is a reasonable value for the springs that we'll be using and the mass that we'll be using. So again, we're using F equals negative, which we'll forget about, kx, where the force, this is the force that pulls on the spring, this is the springiness of the spring, and this is how much we stretch the spring. In English, if you were interested. Part 3. If you were to pull the mass down a bit, then release it, how long would it take to bob up and down once? Okay, so it's obvious to me now that I didn't give you this formula in the previous video. So T equals 2 pi square root of m over k. This will tell us the period of oscillation of a mass on a spring. So, period of oscillation. I saw some funny, I don't know what it was. Oh, it was this physics lecture. And the guy was doing just what I'm doing, and he's saying, oh, period of oscillation is this, and if you don't know what pi is, you should just leave. I thought it was hilarious. So anyway, yeah, that's pi. And mass, and k, so spring constant. So notice how if the mass increases, it takes longer to bob up and down, or to bob up and down. And spring constant, if the spring constant increases and the spring is springier, it will take less time. So let's substitute in and see what happens. If you were to pull the mass down a bit and release it, how long would it take to bob up and down once? So we substitute in 2 pi square root, and our mass was 0.5, and our spring constant was 50. So 2 pi, I'm sure you're calculating this at home, times square root of I'm using Desmos on the computer. This is a little cumbersome. 0.5. Alright, so this says 0.628. Don't believe it. And again, this is a value for time. We're looking for the amount of time it takes to bob up and down once, meaning period of oscillation, 0.268 seconds. Okay, moving on. So this is still related to that previous example. If the mass is pulled down by 5 centimeters, then released, how much potential energy is given to the mass spring system? Aha! Another formula we need. Or wait, oh, maybe I did put this one in. Oh yeah, I remember. Potential energy of the spring, or we could just say PE, 1/2 kx squared. So again, this is the springiness of the spring. This is the displacement from equilibrium. Let's make sure we get the units correct. So we have 1/2, and our spring constant is 50. X, displacement from equilibrium, 0.05. So 5 centimeters, 0.05 meters. Square it, and let's see, 25 times. Ooh, it's going to be a 625 with a bunch of zeros. Let's see. .5 times 0.05 squared, 625.0. So not a lot of joules, but again, we didn't pull the spring very much. Okay, so again, this is potential energy stored in the spring when it is stretched. Alright, we stretch it down, we release it, and then it's going to move back up. So the potential energy down here turns into the kinetic energy at equilibrium, and then would turn back into potential up here. Part, whatever this is, 5. What would be the kinetic energy of the mass as it passes through the equilibrium position? I just kind of gave that away. And how fast would it be going? Well, then we can calculate it. So what we're saying is the potential here, which we just found, equals the kinetic energy as it passes through the equilibrium. This is just like the roller coaster, sort of going up and down where potential turns into kinetic. Potential turns into kinetic, and that we can say that all the mechanical energy is kinetic because none of it, well, because the potential energy is 0 here. That's the equilibrium position. So we can say that was easy to calculate. Thanks. Joules for kinetic energy at equilibrium, and if that's the kinetic energy, we know that will be equal to 1/2 equal and 1/2 mv squared. So if we multiply by 2 and divide by our mass, which was 500 grams, so 0.0625, we're multiplying by 2, we're dividing by the mass, which was 0.5, and then that's equal to v squared, so we're taking the square root. Desmos, what do you say? Must be really boring just watching without actually calculating, so you should definitely be doing that. Alright, 2 times 0.0625, and it's to the square root. That's good. So let's divide by 0.5. Get rid of that stuff. Ah, cool. So this says 0.5. And what we're looking for is the speed. So this would be meters per second. And again, this is for the question up here. And lastly, please make a sketch of position versus time. So let's see, what happens is initially we pull it down and we release it. So if we had position and we had time, here's position, here's time, and what was our period of oscillation from the previous page? I forget. And the problem is if I go back, then, I'm seeing if Desmos has it here. No, it got deleted. If I go back, then the video will stop. So we're just going to say, let's say the period of oscillation, I think it was 0.6 seconds or something. So let's just say this is 0.6 seconds and 1.2 seconds and 1.8 seconds. So our displacement starts at some negative value, and by the time it's gone through one complete oscillation, it will have gone to the maximum upward and then back down to the maximum minimum. That doesn't really make sense, the minimum. So like that, and like that, and like that, and like that. And the other value we know is how much we displaced the spring. So we displaced it by 5 centimeters. So these values here in terms of position, this is equilibrium, and this is negative 0.05 meters, and this is positive 0.05 meters. So we got time, and that's measured in seconds, and again we could put our numbers in here. I think it was this, but I kind of forget. Okay, so that's it for a big example, and I think I actually have a couple more, and we'll do part 4.